So the simplest kind of these kernels is basically the linear kernel. In linear kernel, we take the dot product between two different observations, right? So here in this formula, you can see that we have two different observations. One is represented by x and the other is represented by xi. And remember that these two observations are vectors, right? So we have a vector with the name of x and we have another vector with the name of xi, which are basically representing two different observations, and each vector have a number of values, right? So we are taking the dot product between these two vectors or these two observations, and we are computing this as the multiplication of two observations, which means the dot product of each value of each vector and their summation, right? So this above formula, we can see that the dot product between two vectors, which is x and xi here, is the sum of the multiplication of each pair of input values, right? So as I explained that we have these two vectors here and we are taking the sum of the multiplication of each pair of input value in order to calculate a linear kernel. So this was the most basic kernel which we normally used in simple situations, but when we have a little bit of more complex situation, then we move from simple linear kernel to polynomial kernel. And in polynomial kernel, we can say that a polynomial kernel is a more generalized form of a linear kernel. Why? Because you can see here that the polynomial kernel is very much similar to the linear kernel, but with an addition of an extra term here. So what is this term? We basically call this as the degree of the polynomial, right? So polynomial kernel is the most generalized form of linear kernel and distinguish curved or non-linear input space. So when we have non-linear input space, we basically need to use a polynomial kernel so that we can classify different non-linear sets of data. So here is the formula for the polynomial kernel. You can see we again have two different observations here, like we had in a simple linear kernel where x and xi are two vectors representing two different observations, and this polynomial kernel can be given as very similar to a linear kernel in which we are taking the dot product of these two vectors and their summation, but you can see that we have an additional d term here, which is the degree of the polynomial. So we can have it as 2, we can also have 3. So depending upon the problem, we can select the degree of the polynomial kernel. So it says that here d is the degree of the polynomial, which we need to specify manually in the learning algorithm. So you remember that we have some hyperparameters and we need to select those hyperparameters, the values of those hyperparameters, in order to perform our function, our classifier optimally. So here you can treat this d as a hyperparameter or as a coefficient in which we can select the value, and based on that value our kernel will be classifying those data sets. So the value of this d term, which is the degree of the polynomial, is very much dependent upon the problem and the data set. So these were two basic kernels which we mostly use in nonlinear space, but there is another function which is known as RBF kernel, which is radial basis function kernel, and we also use this in more complex situations. So in RBF kernel, which is mostly used in SVM classification, it maps input space in indefinite dimensional space, right? So here is the formula which basically explains the radial basis function, and you can see we are using an exponential function here, right? And we have you can say we have a linear function or a polynomial function with a degree of 2 here. So it is very much similar, but instead of having the dot product, we are basically computing the subtraction of these two observations here, and we are multiplying this term with a gamma value, right? So again, here the gamma value is our coefficient, or you can say hyperparameter, and the value of this gamma parameter can range between 0 to 1, right? So we can select any value between 0 to 1 for our gamma. we need to manually specify it in the learning algorithm. So as very much similar to the degree of the polynomial, we need to select the value of gamma, and the performance of the kernel will be dependent upon the selection of this value. And normally our default value for this gamma, which is used in most of the cases, is 0.1. So you can try, if you are using RBF kernel for SVMs, you can try with the value of 0.1 initially, but if you have some problems, you can range it from 0.1 to 1, and you need to figure out that which value suits best for your specific problem. As we implemented SVM for linearly separable data, we can implement in Python for the data that is non-linear separable. It can be done by using kernels, right? So you saw that we already discussed some example codes in Python, and I will also upload a Python example which is basically using SVMs to perform classification, and we can use that for linear problems as well as for non-linear problems, but for non-linear problems with the help of some kernel functions. Okay, so now let's briefly discuss some of the hyperparameters or the tuning parameters of an SVM, which can play a very major role in improving the performance of an SVM algorithms. So the most important and basic parameters for SVM which needs to be tuned properly if you want to have optimal performance out of your algorithms, those parameters are kernels, the regularization, gamma, and margin. So these four parameters are the key parameters. If you have selected best values for these parameters, then you can expect your algorithms to work perfectly for you, right? And we call these parameters as tuning parameters in an SVM classifier. And we can vary these parameters to achieve considerable non-linear classification line with more accuracy and reasonable amount of time. So if we have these values perfectly tuned, then we can have higher accuracy rate and in less time. So the computation time can be reduced, and the accuracy on the other hand can be increased if we have these optimally tuned hyperparameters for the SVM algorithm. So let's briefly describe these terms. Regularization, the regularization parameter, which is also termed as C parameter in an SVM, is used for SVM optimization, and it tells that how much you want to avoid misclassifying each training example, right? So you remember that we can have some misclassification. So this term basically tells the SVM algorithms that how much we want to avoid those misclassifications on the training set of data. For larger values of C, so if we select this regularization term C with a higher value, the optimization will choose a smaller margin hyperplane if that hyperplane does a better job of getting all the training points classified correctly. So if the value is large for C, then the optimization will choose a margin with a smaller margin, right? So the margin for the hyperplane will be smaller if the value of C is higher, and you know that what happens if we have a smaller margin. Similarly, on the other hand, conversely, if we select a small value of C, then it will cause the optimizer, or it will cause the algorithm to look for large margin, right? So now it depends that what our problem is and how our data set is distributed, and on the basis of these two things we can decide that either we want to have a larger value of C or we want to have a smaller value of C. The images below are examples of two different regularization parameters, right? So we have two different examples in which we have two different sets of values for C. Left one has some misclassification due to lower regularization value, right? So in this case, the value of C is small, and you can see that we have these two misclassification points here. On the other hand, if we have higher values of C, then we will be making classifier to basically to make an attempt in order to classify these points correctly. Now the third thing is the gamma value. The gamma parameter defines how far the influence of a single training example reaches. With low values, meaning far, and high values meaning close. In other words, a gamma value, if we have low gamma value, the points far away from the plausible separation line are considered in calculation for the separation line, whereas gamma value means the high gamma value means that the points close to plausible line are considered in calculation, right? So if we have a low gamma, like if the value of the gamma is set to very low, for example 0.1, then the points which are far away from our decision boundary, that will also be considered for the placement of the decision boundary, right? But on the other hand, if we select a gamma value which is higher, then only the support vector points will be considered for the calculation or the placement of our decision boundary. So again, this value needs to be adjusted, and it's very critical to have a good gamma value to have good performance.